Okay, so the next part is kind of what we've been building up to in terms of differentiation and graphs, which is stationary points, right? The reason this is what we've been building up to, this is quite a big question in terms of an exam. This is a kind of question that I always say that you want. The reason you want it is because it's worth a lot of marks. And if it's worth a lot of marks, then obviously it's going to be a big part of your final grade. And I don't want that to kind of stress you out, because the beauty of this question is it's the same process, and if you can learn the process that's involved with finding stationary points, then you can get a lot of not easy marks, but straightforward marks. So this is the kind of question that you almost want to look out for in an exam, because you know what you need to try and do, and you can pick up a lot of marks from it. Even if you can't get all of the marks, there's a lot of marks available in these kind of questions, and yeah, you can pick up a lot of marks towards your final grade for it. Okay. It's kind of as it sounds. Stationary points are points on the graph where the gradient is zero. Okay, so it's if you imagine how the graph curves up and down, then it's the points at which it changes almost direction and changes from going up to perhaps going down, or it stops for a moment and pauses almost between going up. Okay, so there's two on this graph. Okay, so that's a stationary point there. That's what we call a maximum turning point, as you've kind of already seen, and you'll see me refer to it as a max TP. And then the one at the bottom there is a minimum turning point, a min TP. Okay, there is a third type. So in the second graph, you've got a minimum turning point at the bottom there. Okay, but you've also got this point here as a stationary point, and it's what we call a point of inflection. This is what I mean by something going up and then we're stopping for a minute before continuing up. Okay, so these are your different types of turning points, or stationary points. A maximum turning point, a minimum turning point, and a point of inflection. So what we're basically looking at, we're trying to draw these graphs. We're trying to learn more about what these graphs look like. In which case, we want to find where these turning points are. Okay, and we do that obviously through differentiation as it relates to gradient, and as the gradient is zero, we can basically use everything that we've done so far, and we can find out where these stationary points occur. Okay, because it's rate of change, the gradient is zero, and all we actually have to do here is similar to kind of some of the last questions we were doing, is we basically substitute a zero into our derivative. So we want to make the derivative equal to zero, and then we can solve it from there. And if we can solve it, then we can find out, as I say, where the stationary points occur. Okay, we're going to have to use something that's called a nature table, though, to look at more detail, because once we know where the stationary points occur, that's all we know. But we don't know what type it is. So we need to delve a little deeper into what's going on around about the stationary point to find out, is it a maximum turning point, is it a minimum turning point, or is it a point of inflection? So what we're going to do is we're going to use a nature table to basically look at what's happening either side of the stationary point. Okay. So we've got a standard parabola here, okay, where we've got a minimum turning point, and that's going to occur when x equals some value a. Okay, so what we basically want to do is we want to find this point, and to do that we would differentiate the equation of the curve first. So just as we've been doing so far, we're going to differentiate the curve first in order to give us an equation that allows us to find the rate of change. But if it's a stationary point that we're looking at, we know that the rate of change is equal to zero. So we set the derivative equal to zero. Okay, in other words, there's no gradient, the gradient is zero, and find the x value at any stationary point. So this will give us an equation which we can solve, and we can find out where that point occurs. Okay. What's going to happen next, we're going to draw this. This is what we call a nature table, and you're going to have to get used to these. You're going to draw plenty of these in the next wee while. And there's basically 3 points, and you're going to have to remember these 3 points, okay, or 3 rows. We're looking at x, so we're looking at the x values, okay, and then we're looking at the derivative, so we're looking at the values of the derivative, and then what we actually want to find from all of this is the shape of the graph around about these different points, okay. So for each point that we're going to find, so this is basically telling us that there is one stationary point, okay? And what we're trying to look at is what's happening either side. So we put our A in the middle. So we're going to have 3 columns on the right-hand side of our kind of titles almost. The middle column is going to be A, okay? And this is the one we know about so far, okay? And it's the ones either side that we want to look at. So we know when x is A, okay? So in this row we've got A. When x is A, the derivative is equal to 0. That's what we found, in which case the shape is flat. Okay, we're going to do something similar either side to find out what the shape is either side of the graph. So we're going to pick a point, and it can be any point, but just make your life easy. Pick an easy one, okay? So a number that's nice to work with. Don't pick something like 0.73. You pick something like 1, 0, 2. Okay, you can even pick things like 10. 10 nice, easy numbers to work with. We can multiply by 10 quite easily, so that's quite a nice, easy number to work with, okay? But for the first part, you're going to have to pick one that's less than your stationary point. So in other words, to the left of where the stationary point occurs, okay? And then we're going to find what dy by dx equals. The main thing we're looking at is it positive or is it negative? Because if it's positive, then the gradient is increasing. If it's negative, then the gradient is decreasing, in which case it tells us the shape, okay? So I'm going to pick a point over here, okay? In other words, a point that's less than a. It can be anywhere along here because you can see that all of these points are going to tell us, hopefully, and this is the fact we've actually drawn the graph here, and the idea of this is that we wouldn't necessarily know what the graph looks like, but I can see from all of these points to the left of the stationary point that all these points are going to indicate a gradient of a negative number, okay? So a decreasing gradient. And then we're going to fill this in an H table. So what that should find, it's going to give us a number, okay? But regardless of what that number is, what we're looking for is whether it's positive or negative. So if I find that that number is -7, or if I find that number is -1, all I'm interested in is the fact that it's negative, because a negative gradient will tell me that the shape is going down. Right, so then the next thing to do is to pick a point after our stationary point. So a point that's bigger than our gradient A, so that's wrong. So it should be something that's greater than A. And then we're going to do the same. We're going to find out what dy by dx equals at that point. So a point greater than A. So if A was, say, 2, I'm going to pick 3, 4, 5, 6, 7, 8, 9, 10, anything that's bigger than that point, and a number that's easy to work with. Because what I have to basically do with that number is I have to substitute it into my derivative and then just get a number for that. And again, all I'm looking for is the fact that it's positive or negative. So we can see here that any point after the stationary point is going to have a positive gradient. Okay, and that's all I'm looking at and all I'm putting into my table. And what that tells me is that the shape of the graph will be increasing. It will be going up the way. And you can see from this, now I've got an idea of what the shape looks like around that stationary point, in which case I can see hopefully that at A, I have a minimum turning point. Okay, so as I say, all of this question is based on the fact that we wouldn't already know what the graph looks like. I'm just using the graph to show you what's happening here. And once I've got this, once I've established this, then I can start drawing the graph, okay, start at least making a sketch of the graph, okay? And that's where that would come from. Yeah. Right, there are 4 potential outcomes from your nature table. So we just looked at a minimum turning point there, okay? But you'd also have a maximum turning point. So again, you set it up in the same way. You'd have your x dy by dx and you have your shape. In the middle column, you'd have your a. You'd already know at that point that the dy by dx was equal to 0, and you'd know therefore that was flat. If to the left of that point you had a positive gradient, that means the shape is going up. And then if to the right of that point you had a negative gradient, that means the shape is going down. So what we have here is a maximum turning point, okay? As we've just looked at, okay, you'd have your A in the middle, you know it's 0, you know it's flat. To the left of it, if it was negative, it's coming down. If it's to the right of it, it's positive, it's going up. That tells you you've got minimum turning point. Okay, the other two that are a little bit different are these two situations here. Okay, so again, set up in the same way, x dy by dx and shape. A0 and flat in the middle, that tells us there's a stationary point, but if to the left of it, okay, in other words, where A is or a number less than A, if it's a positive value that we get, that tells us that the shape before is increasing to that point. Then if we also found out afterwards that it was positive, that means it's increasing after that point, which then tells us it's a point of inflection. More importantly, an increasing point of inflection, okay? And we'd have to draw such in our graph. And then obviously the final version is when we have a kind of a falling point of inflection, okay? But it's the same kind of idea. If we've got our stationary point, if to the left of it, it's decreasing. If it's negative, it's decreasing, it's falling. And then also to the right of it, it's decreasing, it's negative, it's falling. Then we'd have a falling point of inflection, okay? And once we establish what the kind of the stationary point is doing, then we can start to draw it in our graph, okay? Right, you can actually get an idea. You already know what some of these graphs look like. Okay, so more often than not, we're going to be dealing with cubic functions. Okay, and if it's a cubic function, it's kind of like a sine graph, but it's not a sine graph because there's a two turning points, and then it goes off to infinity in either direction. Okay, if it's a cubic function, you know there's going to be 2 stationary points, and even quartic functions, there will be 3. Okay. In which case you need to be a bit more careful with your nature tables, right? You can do one individually, okay? But what you could actually do is you can combine them both together, and you've just got to be a little bit more careful because the idea is you've got to find a point between them. So if you knew that there's 2 stationary points, okay, A and B, for example, okay, then this point, what's happening in between them is important, okay? And when you pick a number greater than A with 2 stationary points, that number can also not be bigger than B. It has to be between these 2 values. So if you kind of squish them together like this, then we want to find a value that's greater than A but less than B. okay? And we want to find out what's happening between these two values, okay? And if it's a cubic function, it will generally look like this. There'll be two stationary points, but you've just got to be careful. Although I said you've got to pick a number that's greater than a, if there are two stationary points, it's greater than a, but also has to be less than b, okay? Right, so let's look at a first example, okay? I think I'm only going to do one example because these are quite long, okay? So we're going to find the coordinates of the stationary points of the curve. Let's find the coordinates at the stationary points. I guess that doesn't make sense. Find the coordinates at the stationary points of the curve with the equation y equals a third x cubed minus 2x squared minus 12x plus 5 and determine their nature. Okay, so this bit's important. This is the bit that tells us whether that we want to find out whether they're maximum, minimum, or points of inflection. It's not just a case of finding the coordinates. Sometimes it might be, but if it's asked you to determine the nature, we need to be more specific. So we're building up to a point where we actually draw these, but just now we're just looking at what the stationary points are. Are they stationary points? Where are they? And are they maximum, minimum, or points of inflection? Okay, right. The first thing you can do here is the fact that it is a cubic. Okay, so the highest power that we have here is 3, which means it's a cubic function, which means we can already have an insight as to what it looks like. Okay, so it's, as I say, it's kind of like a sine wave, but it's not a wave. Okay, it turns twice. There'll be a maximum, there'll be a minimum, yeah, what we're basically trying to do is we're trying to find the coordinates of them. So you can look ahead and you can try to work out what you've got, so you know what your answer is going to be. Okay. So the first thing we want to do is start with our equation and then find the derivative of that equation. So remember, what we're building up to do here is we're trying to find the gradient at certain points. Okay, and if we find the gradient at certain, well, more importantly, what we want to find is when the gradient is equal to 0. Okay, so to be able to do anything in terms of the gradient, we want the rate of change. That means we need to find the derivative. So this is actually a relatively straightforward one because of this third, because we do 3 times by the third, which is just 1. X, drop the power by 1, squared, 2 times by 2 is 4x to the power of 1, minus 12, 5 disappears. Okay, right, so this next line is what I want you to write every single time, and it almost nudges you in the right direction. Okay, so once you get to this point, a lot of people get confused and what am I actually doing now? But the idea is that we're trying to find the stationary point. We know that the stationary points, for the stationary points, the derivative will equal 0. So if you write this out, nice short line, but I just remembered it all the time when I was at your age at school. I'd write this out and it would just nudge me in the right direction for what I need to do next. So for SPs, for stationary points, the dy by dx, the derivative will equal 0. And then it would just give me my equation. And if I see an equation, I know exactly what I need to do. I need to solve it. All right. This is obviously a quadratic, so don't be tempted to add on 12 onto both sides. We need to solve this by factorizing it and then taking our 2 brackets and equaling them both to 0. So in advance, we knew that there would be 2 stationary points. We knew it's a cubic, so we know there's 2 stationary points. So if we're going to solve this equation, we know there's going to be 2 answers. We know from past experience, when we get 2 answers for an equation, it generally comes from factorizing a quadratic. Okay, so x squared minus 4x minus 12. We know we're looking for the factors of 12 to take away to give us 4, 6, and 2. We know that the symbols are different. We know the biggest one is minus, so minus 6 and plus 2. Take each of them, x minus 6 equals 0, x plus 2 equals 0. Solve them individually. If x minus 6 equals 0, then x would equal 6. If x plus 2 equals 0, then x would equal minus 2. So this is where my stationary points occur, but it's the x values of where the stationary points occur. If I'm asked for a coordinate, I also need a y value, okay? So the first thing I want to do is find out what that y value is. So I know that there's a point on this curve when x equals 6. I just need to find what y equals. So I substitute my x's for 6, and then I solve it to find out what y equals. So y will equal a third times by 6 cubed minus 2 times by 6 squared minus 12 times by 6 plus 5. Work that all through. If it's a calculator one, you can stick it on the calculator. If it's not, then you're going to need to do a little bit of working out. But either way, it equals minus 67. And that's our first stationary point, 6 minus 67. Okay, so then I need to find the y value of the second one. It's the same idea, but just substituting my x's for minus 2 this time. Work it all through, and I get 18 and a third. And that gives me my second stationary point, minus 2, 18 and a third. But at this point, I don't know which way around they are. I don't know what kind of stationary points they are. Are they maximum? Are they minimum? I know they're not points of inflection because I know it's a cubic, and I know that a general cubic graph always has a maximum and a minimum, okay? But I don't know which one's which. So I have to delve a little deeper, and I actually need to find what's happening basically either side so I can determine whether they're maximum or minimum, okay? So they're my 2 stationary points. Now I need to draw a nature table, okay? So this is one full nature table. And the idea is that I've got 5 slots, okay? So I want to find out what's happening before the first one. And this is my first one because it's the lowest number, okay? So that goes in minus 2 there. I'm going to find out what's happening between them. The second one is 6. I want to find out what's happening after 6. So I know at these points I have basically the dy by dx, the gradient is equal to 0, in which case the shape is flat. So I already know part of it. It's, as I say, what I'm interested in is what's happening either side and between them. Okay. So the first thing I want to do is pick a value of x that's less than -2. Okay, so -3 is a straightforward enough one. Okay, I think that's what I pick here. Yeah, but you could pick something like -10. -10, but given that we're going to have to put it basically into our derivative, and this is where you need to be careful. It's dy by dx, and this is why I get to write out this in full. So I'm trying to find a gradient. I'm not trying to find what the value of a coordinate, and that's what I'd use this equation for. I want to find a gradient, so I need to substitute into dy by dx. Okay, so I'm looking at that formula. I know there's a squared part to it. If I square it 10, it's going to give me 100. It's a nice, easy number to work with. Okay, but it might be worth just keeping it as low as possible. Okay, so -3 is what I'm going to pick, and I'm going to substitute it into my derivative. Okay, so dy by dx will equal -3 squared minus 4 times by -3 minus 12, which is 9. Right, I don't really care about the fact that it's 9. I'm more worried about the fact that it's positive. Okay, because if it's positive, it tells me that the gradient is positive, okay, which tells me that the shape is increasing. That's what I'm interested in. Okay, so you can go through this and you can kind of almost look and you can think, right, this is going to be a really big number, or this is going to be a really, really, really small negative number. You don't necessarily have to get the full answer. You just need to establish the fact that it's positive. Okay, so that tells me that before this stationary point, it's increasing. Right, so this might tell me, and because I know it's a cubic, it's probably going to tell me that this is a maximum turning point, but just check, okay? Because apart from anything else, you might have got something wrong earlier. Okay, so then we're looking at between -2 and 6. So I want a number that's between -2 and 6. So 0 is an obvious one to pick, okay, because 0 is obviously a very easy number to work with, because if we're multiplying by it, it just stays as 0. Okay, but you could pick 1, you could pick -1, okay, you could pick 2, 3, 4, 5 if you wanted to. Okay, but pick something that's easy to work with and then substitute it into your derivative. So again, the same equation, but just with zeros this time. So dy by dx will equal 0 squared minus 4 times 0 minus 12, which is -12. Again, I'm not really interested in the fact that it's 12. That's not telling me much. It's telling me that's quite a steep gradient, but it's a gradient down the way. It's a negative gradient, okay? In which case it's going down the way, in which case that does confirm what I thought. This is a maximum turning point, okay? But I'm still going to look after 6. Still going to see what's happening. Again, because it's a cubic, I kind of know already that it's going to be a minimum turning point, but I just want to double check just to show that I've got everything correct up until this point. So I'm going to pick a number that's greater than 6. So 7, 8, 9, all fine, but 10, I like working with 10. I'm squaring it, I'm timesing it by 4. It's an easy number to work with. So 10 squared is 100. 4 times by 10 is 40. 100 minus 40 is 60. Minus 12 is 48. Again, not interested in the fact that it's 48. More interested in the fact that it's positive, which does confirm what I thought in the fact that it is a negative, is a minimum turning point, because if it's positive, it's going up after the point 6, which tells me this is the lowest point. It's coming down to that point, going up after that point, in which case it's a minimum turning point. So this is all just working. I've just got to basically write my answer now, okay? In other words, there's a maximum turning point at -2, 18 1/3, and a minimum turning point at 6, -67. So a lot of work to do, working to do all of that, okay? But as I say, you'll be rewarded with a lot of marks, and it is just the same kind of thing every single time,